Hello, is the screen visible and am I audible? So let's just start with the today's lecture. Welcome everyone to the NPTEL course on Introduction to Polymer Physics, which is instructed by Professor Amit Kumar, Department of Chemical Engineering, IIT Guwahati. I am Shikha Sharma, a research scholar in the Department of Chemical Engineering, IIT Guwahati. So I'll be the TA for this course for the July 2024 semester. So this is a live interaction for week 1, which is on the topic Introductory Concepts and Models of Isolated Polymer Chains. I hope you have already gone through the 3 lecture videos related to week 1 topic. So in this live streaming, we will be practicing some of the problems and the concepts behind. And if you have any query, you please feel free to ask. Let's move on to solving the questions, and then we simultaneously we will discuss the basic concepts. So question 1 says, which of the following polymer occurs naturally? Bakelite, Teflon, cellulose, perspex. So what do you think, which of the polymer occurs naturally out of all these 4? Yes, the option C is correct, which is cellulose. So the polymers, we know that there are of 2 different type of polymers, like natural and the synthetic. The natural one are those which are extracted from the natural sources, like the cellulose. It is extracted from the wood or from the fruit pulp or the peel, and then from the bran or the husk of different cereals. So it is naturally occurring. And then the synthetic polymers, they are basically made from the, like, chemically they are made. So the option A, which is bakelite, option B, which is Teflon, and option D, which is perspex, these are basically the synthetic polymers which are chemically made. But the option C, which is cellulose, it is basically naturally it is extracted from the natural sources. Now let's discuss question number 2, which is having column A and then column B, and we have to match the polymer which is there in the column A to its application which is in the column B. So in column A we have several polymers like nylon, polyethylene, cis-1,4 polyisoprene, acrylonitrile, butadiene, styrene. And then option column B is having different applications like television cabinet, tire, mechanical gears, packaging. So these are, which, what do you think, which option is correct? Which polymer is matching with which application? So the option A is correct. And in the table, we can see that there are these 4 polymers, the properties and the applications. Like nylon, it is a strong polymer. So it is used for mechanical gears and the textiles. So for nylon, option 3, which is mechanical gear, is correct. For polyethylene, since it is low cost, high ductile and have high impact strength, so it is used for packaging applications, for making food packaging containers, grocery bags, and then the wash bottles, and then fibers and in the fibers and textiles. So the option 4, which is packaging, is correct for Q. Next is this 1,4 polyisoprene. So it is used for making like it is a synthetic rubber used for making outstanding strengths, like it is having high strength, and then it is having excellent compression set. So it is used for making anti-vibration mounts, drive couplings, tires, springs, bearings, rubber bands, and then adhesives. So for R, which is cis 1,4 polyisoprene, which is also the rubber. So rubber is used for making tires. So option 2 is correct for R. And then ABS, which is acrylonitrile butadiene styrene. It is having high impact resistant and toughness. So it is used for making the television cabinets, automotive vents, pipes, systems, musical instruments, golf club heads, etc. So the option 1, which is television cabinet, is correct for option S polymer, which is ABS. So option A is correct. Now let's discuss question 3, which is the correct order of molecular weight. So there are these 4 molecular weights: Mv, Mn, Mw, and Mz. So we know that polymers are having different molecular weights. Like polymer can be expressed in different weight forms. Like Mn is the number average molecular weight, and then Mw is the weight average molecular weight, Mz is the Z average molecular weight, and or the Z average molecular weight, and then the Mv is the viscosity average molecular weight. So we need to arrange it into correct order of their uh, which is bigger or which is smaller, we need to arrange, and for that option C is correct, which says that Z average molecular weight is greater than weight average molecular weight, and then the viscosity average molecular weight, and least is the number average molecular weight. Why so? Why this is happening? Can anyone please tell me the answer? Yes, the reason is since number average molecular weight formula, these all formulas are available in the lecture slides. I hope you have already gone the lecture slides. There all these formulas are mentioned. So the number average molecular weight Mn is the summation of number of the moles of like A segment in the polymer multiply its molecular weight plus number of the moles of B segment multiply its molecular weight. So all these segments moles will be multiplied by their molecular weight, and then they will be summed up and then divide by the summation of of moles of all the fractions or all the species which is present in a polymer. And then weight average molecular weight, it is a summation of number of the moles into uh, molar mass, but its square is there, and then divide is summation of NiMi, which is number of moles into molecular weight. Viscosity average molecular weight is the summation of Ni moles, which is moles, multiplied by molecular weight to the power A plus 1, divide by summation of NiMi, which is moles into molecular weight. Now the whole is under the to the power of 1 by A. What is A here? A is basically a constant which tells about the linear expansion factor. Like if a like it is basically used when polymers are having some viscosity or polymers are put into some solvent. So there the polymer chain can be expanded or they can be contracted. So A denotes that constant of expansion factor in any like hydrodynamic chain dimensions. in any like when polymer is being put into some solvent, then uh, this constant will be considered. V average molecular weight is the summation of Ni into molecular weight to the power q divided by summation of Ni Mi square. So from all these formulas we can see that the Z is having like MQ. So obviously it's, and that is input in the numerator. So clearly the Z average molecular weight will be like higher than the weight average molecular weight, which is having the square in its numerator. And then rest two are the viscosity average molecular weight, which is having A plus 1, which is more than the 1, because A will be always like positive. So its value will be mostly the positive value. So after that viscosity, so the viscosity average molecular weight, and then the last is the number average molecular weight, because its power is just 1. So because of because we can see their form by their formula that V average molecular weight will be higher than weight average molecular weight, then the viscosity average molecular weight, and least will be number average molecular weight. Now let's discuss next question. And if you have any query, please you can please let me know. Question 4, it's about a polymer sample consists of 3 fractions. Like a polymer is having 3 fractions of different sized molecules or chains having molar masses of 30,000, 40,000 and 50,000 gram per mole. The number of the moles of the respective fractions in the sample are 0.025, 0.020 and 0.005 respectively. So from this question we can see that a polymer P sample is having 3 fractions, like we can consider X, Y and Z. So the molar mass of X is 30,000, the molar mass of Y is 40,000 and the molar mass of Z is 50,000. And then their moles is also given, like 0.025 of X, for Y 0.020 and then for Z 0.005. And this question is having 4 subsections. In one, first it says to calculate number average molar mass, then polydispersity index, after that viscosity average molar mass, and then A value is given for that, which we just discussed. And in D it says to calculate weight fraction of the molecules having molar mass of 40,000 gram per mole. So in the first part we need to calculate number average molar mass. We know the formula that number average molar mass is nothing but summation of Ni Mi divided by summation of Ni. So we have like in the solution we can see that there is this polymer P and it is made up of 3 fractions, chain X, chain Y, chain Z, which is having their molar mass given and their moles given. Now number average molar mass can be calculated as the formula which we already discussed. So from this, like we can see that for sorry now we can see that it's the value is written 0. Sorry. Now we can see that the value is given, that is 0.025 for chain X. So the number of the moles, let me just erase. Yeah, so we can see that this N1 value is given, which is 0.025. So Ni is the moles of chain X multiplied by its molecular mass or the molecular weight, which is already given 30,000. So we will multiply Ni into Mi, which is the chain, the first chain, which is X chain's molecular weight and its moles. They are multiplied, and then the summation is there. The plus sign will be there, which is calculating all of the, which is calculating and the sum of all of the multiplication of Ni, Mi. So second is the 0.02, which is the moles of the chain Y, and multiply its molecular weight, which is 40,000, and then the summation of the Z element, which is 0.05, which is moles, multiplied by its molecular weight, which is 50,000, divide by the total, what is total number of the moles, which is 0.025, 0.020, and then 0.005. So when we do this addition and when we solve, then in the numerator we will get 1800, and then in the denominator we will get 0.005, 0.05. So after dividing and then solving, we get A, which is number average molar mass, as 36,000 gram per mole. So let's discuss the next question, which is like the next part of this question, which is the polydispersity index. So first the question arises, what is polydispersity index? Can anybody tell me, from like who has already gone through the lecture, that what is polydispersity index? Yeah, the polydispersity index is the ratio of weight average molecular weight divided by number average molecular weight. So the next question, which asks also, the polydispersity index may be, it's the value of the polydispersity index can be either like is it lesser than 1, equal to 1, greater than 1, or equal to 0.5. So the polydispersity index, as the formula says, that it is the ratio of weight average molecular weight to the number average molecular weight. And we know that the weight average molecular weight is greater than the number average molecular weight. So the so we can say that either the ratio will be greater than 1 or it is equal to 1. So the option B and C can be correct in this case. And then let's come back to the question B, which is the calculating the polydispersity index. As we already know that the polydispersity index is the ratio of MW by Mn. Here in the segment A, we have already calculated Mn value. So now we need to just calculate MW. Let's see the solution. So MW value is the summation of Ni Mi square divided by summation of Ni Mi. So here we will calculate we know the Ni value for chain X, which is 0.025 into molecular weight square, which is 30,000 square, plus next is the 0.020, which is chain Y molar mass, sorry, moles into 40,000 square, which is chain Y molar mass, plus chain Z 0.005 moles into its molar mass square, which is 50,000 square, divide by summation of NiMi, which is its moles into its molar mass. Like here, this is X, this is for Y, and this is for Z. So after calculating, we get the value of 37,222.22. Sorry, let me erase it. So we get the value of 37,222.22 gram per mole. Next is we need to calculate PDI, which is polydispersity index, and we know this formula already. Now we have already calculated Mn in the previous slide, like this. We have already calculated, and we have calculated MW value. So we just need to divide MW by Mn, and we get the 1.034 as our PDI, which is polydispersity index value. Let's move to the next slide. This section C, which is calculating viscosity average molar mass. When A value is already given as constant 0.6. So from this, which option is correct? Let's just see. So here, I tried to calculate A value. This, sorry. Yeah. Yeah. So in this, let's as we know that viscosity average molar mass formula is already given, which we already know. Right? So as per this formula, summation of Ni moles into its molecular weight Mi to the power A plus 1 divided by summation of NiMi and whole to the power 1 by A. So A means, so here it is written that A plus 1. This is A plus 1. So I tried to calculate A plus 1, which is 1 plus 0.6, which is equals to 1.6. And then 1 upon A means 0.6. So let's just put the values in the equation and then try to calculate viscosity average molar mass. So Ni for chain X is 0.025, its moles, multiplied by its molecular weight, which is 30,000 to the power A plus 1, which is, we just calculated, it is this one, 1.6, right? And then the same we'll do for the chain Y, which is its moles multiplied by its molar mass 0.020 into 40,000 and to the power A plus 1, and for the chain segment Z we will calculate and then we will sum up all these three things, and then we will divide by summation of NiMi, which is this for X, for Y, and for Z we will calculate, and to the power of 1 upon A, which is 1 by 0.6, and just multiplying and then calculating, summing and calculating, we'll get the value of viscosity average molar mass as 36,970.4 gram per mole. So last last segment. So what is the correct answer from 1, 2, 3, 4? What we got is 36,970, which is option A is correct. So now let's move to its subsection D, which asks to calculate weight fraction of the molecules having molar mass of 40,000 gram per mole. So we need to calculate the weight fraction of the molecules, weight fraction, and we have already the molar mass value. So we know that weight fraction means of anything is weight of that particular species divided by total weight, which is like now let's calculate first the total mass of the sample, which is like we will divide at the bottom, like in the denominator, like weight fraction of any species like the species A or species B is equals to mass of that species, like mass of that A or B segment divided by the total mass. So we need total mass for this calculation. So we'll calculate first the total mass of the sample, which is summation of Ni into Mi, which is moles of like all the segments multiply by moles of the segment 1 multiply by its molar mass and then its summation, which is like for chain X its number of moles, which is 0.025 into its molar mass, which is 30,000. Then um, the chain Y moles and its molar mass, and then chain Z moles and its molar mass. We'll sum all these, and then we will multiply, and then we'll sum, and we get the 1800 as total mass of the sample. Now calculate mass of the molecules having molar mass 40,000 gram per mole. The species which is having molar mass 40,000 gram per mole will calculate its mass. So we'll multiply its mole fraction to its molar mass. So we get the mass, which is it's like the N2 species, which is the chain Y, which we have taken. Its moles is 0.02 into its molar mass is 40,000. So after multiplying these, we get 800 gram. Now we need to calculate the weight fraction of the molecules which is having molar mass 40,000, which is like W2, which is the or WY, which is the chain Y weight fraction. So we'll take its mass, which is 800 gram, divide by the total mass of the sample, which is 1800, which will divide, will get 0.44 gram, 44 its fraction. So there's no unit. So 0.44 is the weight fraction. Now let's move on to question number 5, which is about degree of polymerization. So what is the degree of polymerization of each of the following polymers with molar mass 1 lakh gram per mole? So there are these three, we can say three polymers which are named as polyacrylonitrile, polycaprolactam, and then polytrimethylene ethylene urethane. So these are three polymers, and the degree of polymerization is asked to calculate, and then uh, and then already its molar mass is given. So let's just discuss what is degree of polymerization. So the degree of polymerization is basically number of repeating units that constitute a polymer molecule. So it is given by molecular weight of the polymer divided by molecular weight of the monomer. So it basically tells that how many repeating units are there in a polymer. So let's calculate for first polymer, which is polyacrylonitrile. So the polyacrylonitrile monomer unit is acrylonitrile, and it will go under free radical vinyl polymerization, and it will form polyacrylonitrile. So we know the monomer, and from that monomer, which is acrylonitrile, we can calculate the molecular weight by seeing its structure and calculating the number of the carbon atoms or the hydrogen or different atoms in a particular monomer. So we can see from the figure that there are 3 carbon atoms. So 12 into 12 is the molar mass, multiply by 3 is the carbon atoms like molecular weight, contribution for the carbon atom in the total molecular weight. Then is the nitrogen is 1, so 14 into 1, and then hydrogen are 1, 2 and 3, so 3 into 1. So we will calculate, and then the value is 53 gram per mole is the acrylonitrile's molecular weight. Now, for calculating dP, which is degree of polymerization, we will divide the given molecular weight of the polymer, which is 1 lakh, divide by 53, which is its monomer, which is acrylonitrile's molecular weight. So, after dividing, we will get 1887 as the dP, which is degree of polymerization. Now, let's see polycaprolactam, the another polymer. So the polycaprolactam monomer unit is caprolactam, and its molecular weight is, by calculating the different atoms involved in the monomer, which is like the carbon atom are 1, 2, 3, 4, 5, 6. 6 are the carbon atoms, and then the hydrogen atoms are 11, like 2 to 4, 5, 6, 7, 8, 9, 10, 11. And then is the nitrogen atom is 1 here in red, and then last is the oxygen, which is here 16 into 1. So by calculating, we will get 113 gram per mole as a molecular weight of caprolactam. So the degree of polymerization is 1 lakh divided by 113. So the final value is 885. This molecular weight is constant and is given for all the polymers, and we need to see how many like this constant, in the constant weight, how many number of the monomers or the repeating unit can be come in this polymer. So it depends on the, if the molecular weight of the monomer, which is the denominator, is higher, like here 113, and in the previous case it's just 53. So the degree of polymerization is inversely proportional, like it will decrease if the molecular weight is higher, like in the case of polycaprolactam. Next is the polytrimethyl methylene ethylene urethane. So its structure is already given. You can see here. Now the molecular weight of the trimethylene ethylene urethane, we have to calculate. From this we can see that there are 1, 2, 3, 4, 5, 6, 7. 7 are the carbon atoms. Then 1, 2, 2 are the nitrogen, 1 oxygen, 2, 3, and then 4. 4 is the oxygen, so 16 into 4. And then last is the this hydrogen. Hydrogen are 12. 2 to 4, 5, 6, 7, 8, 9, 10 or 11, 12, 1, 2, 7. So 12 are the hydrogen. So after calculating, we'll get 188 gram per mole as the molecular weight of trimethylene ethylene urethane. So the degree of polymerization is 1 lakh divided by 188. So 532 we get the as dp, which is degree of polymerization. As we can see, since the polytrimethylene ethylene urethane's monomer weight is more, so its value is least, which is 532. Then the polycaprolactam, then the polyacrylonitrile, which is having the higher degree of polymerization, means it is having more number of the monomers in its chain, polymeric chain, since and all the monomers are having lesser weight. Now let's just discuss question number 6, which is if 5 gram of a monodispersed polystyrene sample of molecular weight 10,000 gram per mole is mixed with 15 gram of another monodispersed polystyrene sample of molecular weight 20,000 gram per mole, then what is the polydispersity of the resulting mixture? So it is given in the question that there are there are two monodispersed polystyrene samples. One is having 5 gram weight and its molecular weight is 10,000, and which is mixed with the another monodispersed polystyrene sample and form the which is having 15 gram weight and molecular weight is 20,000 gram per mole, and these both are combined to form the final mixture. So the polydispersity we need to calculate of the resulting mixture. So let's just see the solution as it is given. 5 gram polystyrene sample which is having 10,000 gram per mole is mixed with 15 gram polystyrene sample which is having 20,000 gram per mole is giving the final mixture. So we need to calculate the PDI, which is polydispersity index. So we know that polydispersity index is the ratio of weight average molecular weight to the ratio of number average molecular weight. It is already we know from the formula. So we need to calculate the weight average molecular weight and number average molecular weight in order to know the PDI. So for calculating these two weights, we need moles of A and moles of B. So the moles of A is equals to the gram of the sample which is given to the molecular weight, which is 10,000. So 5 divided by 10,000 this will give the moles of A polystyrene sample A, and then moles of the polystyrene sample B can be calculated by dividing 15, which is the gram weight given, divided by 20,000, which is the um, polystyrene sample B molecular weight, and we get the moles of and of B sample. So it is NB, and now we'll calculate first the Mn value, which is nothing but summation of Ni Mi divided by summation of Ni. So from this we can say that Mn is equal to 5 divided by 10,000, which is the Ni value, which is Na value, for the polystyrene sample A, into its molecular weight, which is 10,000, plus 15 divided by 20,000, which is the moles of B, polystyrene sample B, into 20,000, which is the molecular weight of B, divided by summation of Ni, which is moles, 5 by 10,000 and 15 by 20,000. Now we'll calculate, solve the problem, solve it numerically, and we'll get the Mn value as 16,000. Now calculate Mw value, which is nothing but the summation of Ni Mi square divided by summation of Ni Mi. So for polystyrene sample A, the moles equals to 5 by 10,000 multiplied by its molecular weight square, which is 10,000 square, and then the chain for similar will be done for chain sample B, polystyrene sample B, which is 15 divided by 20,000, which is the moles, into 20,000 molecular weight square, and then in the denominator it will be in the denominator summation of Ni Mi will be calculated, which is 5 by 10,000 multiplied by its molecular weight, which is 10,000 for A, and then moles of B, 15 by 20,000 multiply by its molecular weight 20,000. We'll solve and we get the value as 17,500 MW value. Now for PDI, we'll divide MW by Mn, which is 17,500 divided by 16,000, and we'll get 1.09. So we can see that the PDI value is greater than 1, which is 1.09. The same like it validates this question which we already discussed previously. This one. Here also we got 1.034, which is greater than 1. So this question, that either it is equals to 1, PDI is equals to 1, or it is greater than 1, is clearly seen. Now move on to question number 7, which is about the homopolymers. So now let's first start with the discussion of the classification of the polymers. So the polymers are basically the linear chains or the branched chains, and it is also, in as per the another classification, it can be homopolymer or it can be copolymer. So first let's discuss what are homopolymers. So homopolymers are basically, they are made from many copies of a single repeating unit. So the repeating unit, which is the monomer, it is the single. It cannot be more than one. So now let's come back to question, that among the following, which one is homopolymer? So the option A says neoprene, or B says Tyrlin, C says nylon 66, and D says nylon, none of the above. So let's discuss the solution. So what do you think, what should be the answer? So let's move to the solution. So option A, which is neoprene, is the homopolymer, and rest are others are not the homopolymers. So let's discuss why, what is the reason behind this. So as we see in this diagram, the neoprene is the homopolymer which is made of the single repeating unit which is chloroprene. So only the chloroprene monomers, they are combined and they will polymerize and they will form the neoprene polymer. But in the case of like tyrrolene, as we can see in the structure, that two monomeric units which are ethylene glycol and terephthalate acid, they are these two monomers, they'll combine and they'll polymerize and they'll form the tyrrolene, or the which is also known as dacron. So it cannot be true because it is a copolymer, or it is not made from a single monomeric unit, it is made from two monomeric units. So next is uh, nylon 6,6. Option C is nylon 6,6. So the nylon 6,6 is made from adipic acid and then hexane diamine as its monomeric units. These two monomers, they will go in the in the condensation polymerization and they will form nylon 6,6. So due to having more than one monomeric unit, it cannot be homopolymer. So this cannot be homopolymer. So neoprene is the correct answer. Now let's discuss question number 8, which is about linear low density polythene, which is LLDPE. So it discussed that LLDPE is a copolymer of ethylene and a small fraction of, so it is saying that LLDPE is a copolymer of which is formed from the two monomeric or more than like one monomeric unit, uh, out of which one is ethylene and this next is uh, like it is asking. So the option A says butadiene, option B says isoprene, C is butene and D is hexadiene. So let's first discuss what is copolymer. Already we have discussed that polymer is classified into homopolymer and copolymer. Homopolymers are having one monomeric unit. So what is copolymer? So copolymers are made up of two or more monomeric units. So it is having more than two or more than two monomeric units, which we can see in the previous slide that tyrrolene is made up of two monomeric units, which is ethylene glycol and terephthalic acid. And the nylon 6,6 is also made from two monomeric units, which are adipic acid and hexane diamine. So these two are copolymers. So copolymers can also further classified into block copolymers, random copolymers, alternate copolymers and the graft copolymers. So let's come back to the question. And all these concepts, like these different types of copolymers, these are discussed in the lecture videos in detail, and in Manish Chandra book also, like it is explained in detail with the pictures, so you can please refer those notes. Now let's come back to the question that LLDPE is a copolymer of ethylene, and which option do you think out of these four should be correct? So the answer is butene. Why butene? Why not others? Let's just see. So LLDP is synthesized from two monomeric units, which are ethylene and 4-methyl 1-pentene. This is alpha olefin. This is of the category of alpha olefins. So what are when ethylene is combined with the alpha olefin, any monomeric unit from the alpha olefin group, in the presence of Ziegler-Natta as catalyst, it will polymerize and form the LLDP. So, from this alpha olefin group, why it is called alpha olefin? So, it is called alpha olefin because at its alpha carbon, we can see there is this double bond. So, they, uh, so these are called alpha olefins. So, from this category, there are different monomeric units can be there. Like we can see here butene, hexene, octene, decene, etc. But out of these, only butene is there. So we can say that the butene is the one which is the copolymer, one of the monomer of the copolymer LLDPE. Now let's discuss question number 9, which is the numerical problem on the copolymer. So, a random copolymer consists of the following two repeat units in 6:4. So, one repeat unit is this and the another repeat unit is this. So, first repeat unit is, we say that it's a monomeric unit is consisting 60% weight of the total polymer, while the monomeric unit B, it consists around 40 weight% of the total polymer. And then it is given that number average molar mass of the copolymer is 50,000 gram per mole, and the number average degree of the polymerization of the copolymer we need to calculate. It's not given, right? So we need to calculate this. So now let's move to the solution. So we have these two, we know the structure of these two A and B monomeric units, and we know that A is around 68% of the total polymer and copolymer, and B is around 40% of the total copolymer. And the number average molar mass of the copolymer is already given, which is 50,000 gram per mole, and the number average degree of polymerization of the copolymers is needed to be calculated. So, since we know the structure already, this is the structure of A type of the monomer or A type of the repeating unit. So, we can easily calculate its molar mass based on the structure and what are all the different atoms there in its monomeric unit. So, molar mass of the A type of repeat unit, which is M1, we are denoting it by M1, is equals to, like, first we calculate number of the carbon atoms, which is 1 here and 6 here. So total 7 number of the carbon atoms are here. 7 into 12 plus 1 is the nitrogen atom. So 14 into 1, and then there is 1 oxygen atom. So 16 into 1, and then there are 13 hydrogen atoms. So 13 into 1. So when we do the multiplication and afterward the summation, we'll get 127 gram per mole. Similarly, we will calculate molar mass of B type of the repeat units. So, we know the structure of B type of repeat unit, which is also which is having 40 weight, contributing to 40% of the uh, total copolymer. So since we know the structure, we know the what are the different atoms in the structure, and we can calculate the molar mass of B type of repeat unit. So there, how many carbon atoms are there? One here and 6 in the benzene ring. So totally 7 into 12 is carbon atom, and then 1 is the oxygen atom and 1 is the nitrogen. So 14 into 1 and 16 into 1. So and now hydrogen atom. So there are total 5 hydrogen atoms. After after multiplying and summing up, we get 1.9 gram per mole as the molar mass of B type of repeat unit. So the weight fraction, now we have to calculate the weight fraction of A type of repeat unit, which is denoted by W1. So we know already that the weight fraction is 60% weight percent. So 60 divided by 100, which is the weight fraction, is equals to 0.6, and it is equals to N1 M1 divided by N1 M1 plus N1 N2 M2. So here N1 is the moles of A type of repeat unit multiplied by molar mass of A type of repeat unit divided by N1, which is moles of A type of repeat unit multiplied by molar mass of A type of repeat unit, plus N2, which is moles of B type of repeat unit multiplied by its molar mass, which is B type molar mass of B type of repeat unit. So for calculating the for calculating any of the weight fraction, like if we calculating weight fraction of type A repeat unit, then it will be the it will like N1 M1 by N1 M1 plus N2 M2, and it is the 60 weight percent is already given in the question, so we have written 0.6. If uh, we need to calculate the weight fraction of B type of repeat unit, so we could have written W2 equals to 40 weight percent, means 40 divided by 100 is equals to N2 M2 divided by N1 M2, N1 M1 plus N2 M2. So here now we are now the weight fraction of A type of repeat unit, we will divide the numerator and the denominator by N1 plus N2, and we are doing it so that we can convert the formula of weight fraction into the mole fraction formula. So here when we divide the numerator and denominator by N1 plus N2, we are getting x1 and x2 here in the formula. So here x1 is the mole fraction of A type of repeat unit multiplied by molar mass of A type of repeat unit, which is already we can calculate based on the chemical structure or the chemical formula of the different monomers, and then x divided by x1 m1, which is mole fraction of A type of repeat unit multiplied by its molar mass of A type of repeat unit plus X2 M2, which is mole fraction of B type of repeat unit, multiplied by molar mass of B type of repeat unit, is equals to 0.6. So we are just, what we are doing is we are just converting the weight fraction formula of A type of repeat unit into the mole fraction formula of A type of repeat unit, and then by this we can solve and we can get this, like we can put the values which is m1 value we have already calculated as 127 and m2 value as 119. So we will put these values in the formula and then we can solve it, and here I am converting x2 into the x1, like here I am converting and I am writing x2 equals to 1 minus x1, and since I want to calculate one of the unknown value which is x1, so I am converting this formula into the terms of x1. From this calculation we can get x1 equals to 0.5843. So I have already got the mole fraction of A type of repeat unit. From this we can calculate x2 value, which is 1 minus x1, which is 1 minus 0.5843, and we can get the mole fraction of B type of repeat unit. And now let's see, here from this formula we already got 0.4157 as x2. The question demands to calculate the number average degree of polymerization of the copolymer, so which is equals to number average molar mass of the copolymer, which is already given in the question as 50,000, divided by mean repeat unit molar mass of the copolymer, which is we will calculate here and we'll put. So how to calculate mean repeat unit molar mass of the copolymer? So its formula is here, and this formula is already shared in the lecture. We just need to apply this formula. So M copolymer, the mean repeat unit molar mass of the copolymer is equals to summation of x into x IXJ, which is the A type, like if I am taking two repeat units, so XA, which is A type repeat unit mole fraction into its molar mass, plus B type of mole fraction of B type of repeat unit into its molar mass. So it is equals to, we know that mole fraction of A type of repeat unit is 0.5843, and we have already got the molar mass, which is 127, and same we will do like for the B type of repeat unit, and we will multiply and this add and we get the mean repeat unit molar mass of the copolymer as 123.67 gram per mole. Now for calculating number average degree of the polymerization of the copolymer, we need to divide 50,000, which is already given as the number average molar mass of the copolymer, divided by what we got 123.67, which is the mean repeat unit molar mass of the copolymer. As we have already seen in the formula, that degree of the polymerization means how many repeat units or the monomeric units are there in a polymer, in a particular gram of the polymer. So here if we divide, we get 404. So 404 repeating units of A and B, which is having 60% A and 40% of B, is there in the polymer. Now let's move on to the next question, which is question number 10. And this question number 10 is about the isomerism, the geometrical isomerism or the cis-trans isomerism. So we have already like discussed in the lecture slides that what is isomerism. So the isomerism is basically when more than one compound are having the same chemical formula but they have the different chemical structure, then it is known as a isomerism. And then isomerism are basically they are divided into constitutional isomerism, which is also the sequence, the second one, the sequence isomerism, which is head to tail or head to head isomerism. And the second is the configurational isomerism, which is which can be either geometrical isomerism or the cis trans isomerism, and it can be optical isomerism or the stereo isomerism. And if we see what is the geometric in the structural isomerism, it is also known as the geometrical isomerism or the cis trans isomerism. In this, what happens actually is there is this double bond. So, so there will be rotation around the double bond, and because of the rotation around a double bond, the pendant like the pendant group, it changes its position. And if uh, the because of the rotation of the double bond and changing of the changing of the structure, if the two non-superimposable images form, then it is the geometrical isomerism or the cis-trans isomerism. And in the stereo isomerism, which is also known as optical isomerism, there should be a chiral carbon atom, so that it shows the optical isomerism. And in the stereo isomerism, like what happens is it is like based on the tacticity, it is further divided into three type of polymers, which is isotactic, symbiotic and atactic. And like uh, uh, yeah, like in the question below, it is asked that which of the following kind of the polymers are known for their high crystallinity. So, options are isotactic, symbiotic, atactic, or none of the above. So, what do you think which is the correct answer? So, in this, the correct answer is isotactic. So why isotactic is because in isotactic, what happens is the pendant group on the one side of the it is on the one side of the hydrocarbon chain, and because it is in the one side, the structure of isotactic polymers, they are very organized and aligned, and they are having tight packing. So because of that, the crystallinity is very high, and it also shows high melting point and the high Tg value. Whereas in the case of the symbiotic, the pendant groups, they are in the alternating position, and in case of the atactic, they are the pendant group are randomly arranged on the side, like on the side of the hydrocarbon chains. So because they are not properly arranged, so their crystallinity will be lesser, and their melting point will also be lesser. So we have discussed about isotactic, symbiotic and atactic, and we have discussed about the geometrical isomerism, which is also known as the cis-trans isomerism. Now let's move back to the question. Number 10, which of the following polymers can exhibit geometrical or cis-trans isomerism? The option A is polyethylene, B polypropylene, C polystyrene, D polyisoprene. So what do you think which is the correct answer? So let's just solve this question. Yeah. So the answer D is the correct one. Now let's just see why polyisoprene is the correct one. So here on the right hand side we can see the structure of polyethylene, polypropylene, polystyrene and polyisoprene. So in the case of polyethylene, here is the four functional groups which are hydrogen atom. So when there will be the rotation around the C double bond C in the ethylene molecule, then due to the rotation, uh, because of the same pendant group, the non-superimposable image will not going to form. So it is not showing so it will not show geometrical isomerism or the cis-trans isomerism. While polypropylene and the polystyrene, they are basically, they are having this C rotation. When they'll have this C rotation, they have three side hydrogen atoms. Here also in polystyrene, three hydrogen atoms are there. And in polystyrene, one is the benzene ring, while in polypropylene, this is the methyl group. So only one group is different and the rest three are hydrogen. So when there is the rotation of the C double bond C, then there will not be formation of the non-superimposable image, and thus it will not be showing they will not show the geometrical isomerism. So here is cancelled, here it is cancelled. So in the polyisoprene, if we see one group is CH3, one is hydrogen, so and rest two are CH2, CH2. So since there are at least two different groups, so when there is a rotation around this carbon-carbon bond, there is when these two functional groups which are same, they are at the same side like here, and these CH3 and H are at the same side, then it forms cis 1,4 polyisoprene. And if it will rotate, it will form non-superimposable image. Next is here, like before it was like this, and now in the trans form, the hydrogen atom is here and the CH3 is here. Now due to the rotation in the C double bond C, we can see a different structure and the non-superimposable structure after rotation, because here these two groups are at the same side, while in the trans they are at the opposite side and they form a different chemical structure. So it is the polyisoprene shows the cis trans or the geometrical isomerism. Now we will discuss question number 11, which is the most stable conformation of N-butane is. Options are eclipsed, skewbot, staggered anti and gauge. So since the polymers or the monomers, they are basically can be in different conformation they can be there, different chemical structures they can be present, and uh, the most stable or have the stable which is having the lesser energy will be a mostly found because it is stable. And we need to see in this question that N-butane, it's what is its most stable conformation. So let's see by drawing its structure. So in this question, the option C is correct, which says that the staggered NT is the most stable. When we draw this conformation of N-butane, we can see like this is the structure. The carbon atom 1 and 4, if we see in the eclipsed structure, which is at the 0 degree, both of the methyl group, they are very near. So because these two bulky groups, they are near, so there will be more repulsion of the methyl groups, and that's why it is unstable. When there is a 60-degree rotation of the methyl group from here to here, there is comparatively lesser repulsion than eclipsed, but it is also having this repulsion force. And then if we further move CH3 to the 120 degree, like from here to here, then due to the like these groups, two methyl groups are very far, so they can, so there is the less repulsion. But here if we see CH3 and H, these atoms are, these groups are very near, so these can repel. Next is the anti. In this 180-degree rotation is there, like from here CH3 moved here, and there is the maximum they are apart from each other, and there is no H group also to so that the repulsion is there. So this anti staggered anti is the most stable configuration, as like we can see anti-staggered is the most stable than gauge because of less repulsion between the methyl groups, because there is the least repulsion, so it is the most stable form. Now let's discuss question number 12, which is about the different polymeric chain models. So there are different polymeric chains models which are named as hindered rotation chain model, the ideal chain model, which is the freely jointed chain model, and then there is the freely rotation chain model. So there are different chain models, and these all are discussed in detail in the lecture slides, and it is very important topic to understand also. Here if we see in the figure, this is the bond length, this is the bond length, and then theta is the bond angle, and psi is the torsion angle. So the question says that in the hindered rotation chain model, what restricts the rotation of the segments? So option A says fixed bond angles, B fixed bond lengths, C energetic barriers due to steric hindrance, and the option D is interactions with the solvent molecules. So what do you think, which is the correct answer? So it is a hindered rotation chain model in which something is hindered, right? So what is hindered? What is restricting? The chain rotation is restricted. The rotation of the segments are restricted in the hindered rotation model. So what is restricting that? Now let's discuss the solution. Option C is correct, which is energetic barriers due to steric hindrance. So, uh, in the like the bond angle and the bond length is fixed in the hindered rotation chain model, which is true, but it is like asking the reason that the what actual element is restricting the rotation of the segment. So why the segmental motion is restricted is because there is the energetic barriers due to steric hindrance, which is because of the maybe because of the uh, other groups. So option C is correct. Option D cannot be correct because here interaction with the solvent molecules, which is not like it is relevant, but it is not very much related to this. Now let's discuss question number 13, which is what is the assumption? What assumption does the freely jointed chain model makes about the bond angles between segments? So there are two different models which are freely jointed chain models, and then second is freely rotating chain model. So here we are discussing about freely jointed chain model, and it is asking what assumption does the freely jointed chain model make about the bond angle between the segments. So it what like how its bond angle behaves, it asks about that. So option A is bond angles are fixed. These bond angles are random. Bond angles are at 90 degree and bond angles are at 180 degree. So what should be the answer? So the option B is correct. The bond angles are random. In option A, C and D, actually bond angles are fixed. But if we see the freely jointed chain model, the bond angles are basically random because in the freely, as the name said, freely jointed chain. So in this, the there is no there is no bond angle and it is free to rotate, free to move. So the bond angles are here random. That's why it is called simple random walk model also, because it is the simplest model, and there here the polymer can walk randomly and have the bond angles random. So it is known as simple random walk model. Question number 14 is related to the freely rotating chain model. So we are discussing so many chain models. Now this asked finally that what is the primary difference between freely rotating chain model and the freely jointed chain model. So the option A says freely rotating chain has fixed bond angles. D is freely rotating chains has variable bond angles. C is freely rotating chain segments cannot rotate. D is freely rotating chain segments have fixed bond angles. So the freely rotating chain model is different from freely jointed chain model, and the freely jointed chain model is basically the ideal chain, which is the it can be it can randomly it can walk, and it should not have the fixed bond angle. Its bond angle can be random. So the option here is in the freely rotating chain, the bond angles are fixed because in freely rotating chain, it is more near to the real chain models, while in the freely jointed chain models, it is the ideal chain. and in most of the real chains, the bond angles are basically fixed. So the option A is correct. The polymer segments in the freely rotating chain, they are having the fixed bond angles to the neighboring units because of the having the specific chemical bonding. And under this fixed angle, the segments are still free to rotate and all the torsion angles are equally likely. So here in freely uh, rotating chain, it is also freely word is there. It is having the free rotation and everything, but it is having the fixed bond angle. Like the bond angle is fixed, but like it can freely, its segments can rotate. But in the case of like we already discussed, freely jointed chain model, it is a ideal chain. Like it can walk randomly and its bond angles are also random. Next, let's move on question number 15. So question number 15 asks about the characteristic ratio for the freely rotating polymeric chains, and here angle is already bond angle is already given, which is 70 degree between adjacent bond vectors. So here in this question, the character we need to calculate the characteristic ratio for the freely rotating polymers chain. So we know already, we have just now discussed that freely rotating polymers chain are having the bond angle fixed, which is already given in the question that it is 70 degree. So we need to calculate the characteristic ratio. So what is the characteristic ratio? The first question arises is this. So the characteristics ratio is actually the it is actually for a polymeric chain, it is the ratio of the mean square end-to-end distance of the real chain to that of a freely jointed chain with the same number of the main chain bonds. Like the characteristic ratio is basically the ratio of the dimensions of the real chain, which is the mean square end-to-end distance of the real chain to that of the freely jointed chain, which is the ideal chain. Like it is the ratio of the chain dimensions for the real chain compared to the uh, freely jointed chain. So as we know, freely jointed chain are basically the ideal chains, and then it is the ratio when there is the same chain bonds, the same number of the chain bonds. And so these are different formulas which are already given, and these formulas, they are already discussed in the lecture videos, and like the characteristic ratio for different models are different. Like for freely jointed chain model, the characteristic ratio is equals to 1, and for freely rotating chain model, which is more more near to the uh, near to the real chain model, so its characteristic ratio is 1 plus cos theta divided by 1 minus cos theta. And third one is the hindered rotation model. So here the characteristic ratio is 1 plus cos theta divided by 1 minus cos theta multiply 1 plus cos phi, which is the torsion angle, and then divide by 1 minus cos phi, which is the again the torsion angle. So these all formulas are different for different chain models, and here in this question, as it is given that it is freely rotating polymeric chain, so the we can apply the formula number 2, which is this. Here The characteristic ratio is equals to 1 plus cos phi. So here it's not phi, it's theta. So 1 plus cos theta divided by 1 minus cos theta. So theta, it is already given as 70 degree. We'll put the value 1 plus cos 70 divided by 1 minus cos 70, which is equals to 2.04. So the answer is 2.04. Now, so in this question, polymeric chain dimensions are given, which are contour length, mean squared radius of gyration, mean squared end-to-end distance are given, and it is asked to arrange from the smallest to the longest, like order these from smallest to the longest. Option A says contour length is the smallest, afterwards mean squared radius of gyration, afterwards mean squared end-to-end distance is the maximum one. Option B says contour length is the maximum, afterwards mean squared radius of mean squared end-to-end distance, and least is the mean squared radius of gyration. Option C says contour length is the maximum, afterwards mean squared radius of gyration, and least is the mean squared end-to-end distance. Option D says mean squared radius of gyration is the maximum, afterwards mean squared end-to-end distance, and smallest is the contour length. So what like these all time we need to arrange these polymeric chain dimensions in the correct order. So any idea, any guesses which option should be correct? So now let's move to the solution, which is B is correct. Now understand the reason why B is correct is because like B says that contour length is maximum, afterwards mean squared end-to-end distance, and then mean square radius of gyration. So as we know from the formula which is provided in the lecture slides in the NPTEL portal, that mean squared radius of gyration is equals to mean squared end-to-end distance divided by 6. So it says that uh, by this formula we can say that mean squared end-to-end distance is more than the mean squared radius of gyration, which is like this part is true. Now let's compare contour length and mean squared end-to-end distance. So contour length, as we know that contour length is basically the length of the entire polymeric chain, the entire backbone chain of a polymer is the contour length. So it will be the maximum and it will be more than mean squared end-to-end distance. So the option B is correct. Now let's move on to the next question. Question 16 says that we need to consider an ideal linear polymer molecule which is having 5000 backbone bonds. Means its n value is already given, that is 5000. The bond length, which is CC bond length, is given 1.54 angstrom. The angle between adjacent bond vectors is 70.5, which is theta value is also given already. Now assume that the polymer chain are described by freely rotating model. So what we just now discussed, that in the freely rotating model the bond length and the bond angles are fixed. So here theta is already fixed, which is 70.5. Now let's discuss the subsection of the question, which asks a part asks about mean square radius of gyration value, B part asks about maximum end-to-end distance, and third parts asks cone length value. So let's just begin by solving part A, which is mean square radius of gyration. We need to compute, we need to calculate, provide, and we have the data provided that it is a freely rotating model which is having CC bond length as 1.54 and theta value as 70.5 and n is 5000. So we know that mean square radius of gyration uh, formula we know already, like in this solution slide we can see that mean square radius of gyration is equals to mean square end-to-end distance divided by 6. So which is the this formula is also applied in previous question here, that that's why the mean square end-to-end distance is greater than mean square radius of gyration. So we can see we need for calculating radius of gyration we need mean square end-to-end distance, and for calculating mean square end-to-end distance we need characteristic ratio value, we need n is already given as 5000 in the question, and L square, L is also given in the question which is 1.54 angstrom. So for calculating characteristic ratio, we need to put the formula for freely rotating chain, as in the question it is provided that this polymeric chain is a freely rotating chain model. So let's solve the question by first calculating the characteristic ratio. So so we have this formula for characteristic ratio in the freely rotating chain model, which is nothing but 1 plus cos theta divided by 1 minus cos theta. So the characteristic ratio is equals to 1 plus cos 70.5, as we already know the theta value from the question. Now in the denominator 1 minus cos theta, which is 1 minus cos 70.5, we'll put the value and then the value of the characteristic ratio will come as 2.002. Now calculate based on the C infinity or the characteristic ratio, we can calculate mean squared end-to-end distance, which is the multiplication of characteristic ratio into n into L square. So here we can just put the values, all the values are already given, and our value after calculation will come as 23,739.7 angstrom square. Since it is a mean square end-to-end distance, so angstrom square is there. Now to calculate mean square radius of gyration, we need to divide this value of mean square end-to-end distance by 6. Here we can just simply put the value and calculate. So our answer is 33,957 angstrom square. So we can here put in this blank our value 3,957 angstrom square. Now second part is asked to calculate the maximum end-to-end distance. So for calculating maximum end-to-end distance, which is R max, we are having one formula which is R max equals to n into L cos theta by 2. This formula is already discussed in the lecture slides. So the maximum end-to-end distance for chains having fixed angle between adjacent bond vectors theta is given by this formula, and it is for this formula applies for the fully stretched chain. R max when R will be maximum, when the chain will be fully in the fully stretched chain. So when chain is fully stretched, we get the R max, and then R max formula, it is already provided. We just need to put the values, which is n equals to 5000, then L is 1.54, and then cos theta by 2, which is 70.5 divided by 2. So just we can calculate the value, and the value, final value, R max value will come as 6288 angstrom. So next part, which is talking about cone length. Now let's discuss. First, the question arises, what is cone length? So here in this question, it asks, it is giving some options. The cone length of a polymer chain is defined as option A, the average end-to-end distance of the polymer; B, the length of the fully extended polymer chain; C, the hypothetical segment length of an equivalent freely jointed chain; or the option D, the radius of gyration of the polymer. So, in your opinion, what should be the correct answer? Yes, so let's discuss what actually cone length is. Like this, in this, the option C is correct, which is the cone length is the hypothetical segment length of an equivalent freely jointed chain. So so we can say that the cone length is basically, it is considered for the real polymer chain, in which there are these n segments which are connected by the cone length, which is B. So each cone segment can be thought as if they are in the freely jointed model, and they are freely jointed with each other and can randomly rotate in any of the direction without the influence of the any of the forces. So the cone length is basically in the freely jointed chain, the model, and there is no as such like force, influence of the force is there, and chain can freely rotate in this, and we can say the option C. That's why we can say the option C is correct, that it is a hypothetical segment of the length in which equivalent freely jointed chain model. And the other option, like C, D option cannot be correct, because radius of gyration of the polymer is something different. Like we already discussed, uh, B says the length of fully extended polymeric chain. So we already discussed that in the fully extended polymer chain, R is equals to R max. So it cannot be equal to cone length. So this option will also be incorrect. And first is the average end-to-end distance of the polymer. So it can also be wrong. It cannot, these A, B and D cannot be correct of because these are these are talk about some different lengths, while C is the correct option. So let's move to the next question. Sorry. Then let's move to the question number C, the section C, which we were discussing before, that calculating the cone length in the previous question. So cone length form, we need to calculate cone length. Cone length is nothing but B value. So to get this formula, which is B equals to mean square end-to-end distance divided by R max value. From this we can calculate B. But For getting this formula, we need to know two other formulas, that the length of a fully stretched chain is for the cone segment chain is equals to NB equals to R max. Like when polymeric chain is in the fully stretched condition, then cone segment chain can be it can be NB equals to R max because it is in the fully stretched position. But when we calculate average end-to-end distance, then it is average end-to-end distance is R square equals to NB square is equals to characteristic ratio into N into L square, which is already, these formulas are already discussed before, and this R square equals to characteristic ratio into N into L square is already just now we discussed in the previous slide. So from these two formulas, we can calculate the value of B, which is equals to mean square end-to-end distance divided by radius divided by R max value. So for calculating B, we need these two values, but we know already that R max is calculated in the previous slide, like here, which is nothing but NL cos theta by 2, and its value, since N is given, L is given, and theta is given, so we already calculated R max as 6288 angstrom. Here now we need we have unknown parameter, just mean square and end-to-end distance. So it can, we can calculate it by calculating characteristic ratio, which is in the previous slide 2.002 multiply by n, which is 5000 given in the question, and then multiply by 1.54 square equals to this value, which is mean square end-to-end distance. Now we can just, for calculating cone length, we can just divide these two values and we can get 3.78 angstrom as our cone length. Now question number 17 we will discuss now. In question number 17, it says that for a polymer in a good solvent, how does the radius of gyration Rg scale with the number of monomers n? Option A, radius of gyration is directly proportional to number of monomers to the power 0, second to the power 1 by 2, third to the power 3 by 5, D to the power monomer to the power 1. So in this question, it talks about when a polymeric chain is dissolved or mixed in a solvent, then how the radius of gyration will change and how it will be correlated with the number of monomers n. So can anybody tell this question, can solve this question? So yes, option C is correct, which is Rg is directly proportional to n to the power 3 by 5. Now let's discuss why it is correct. So what happens is when a polymeric chain is mixed with any solvent, then based on the behavior of that polymeric chain in the solvent, it uh, it will change its it will either contract or it will expand. The chain will either it will be in the expanded conformation or it will be entangled or coiled. So like when we put the polymeric chain in the good solvents, so what happens is the solvent will goes in between the chain and it will uh, create more distance between the chain, and because of that the like it forms the expanded conformation of the polymeric chain. As polymer goes between the chain will expand. While in the case of the theta solvent or the ideal solvent, when the polymer is mixed with the solvent, there is no effect on the chain radius, or the chain will neither it will expand nor it will entangled or foiled. But in the case of the poor solvent, since it is a poor solvent and polymeric chain doesn't like it, so when polymeric chain is mixed with the poor solvent, the polymeric chain will try to foiled and entangled, and it will try to avoid the interaction with the poor solvent. So its wall dimension will be in the contracted form, and it will be entangled or the foiled. So option C, which says that in the in this question it says that there is a good solvent. So what will going to happen is the polymer chain will be in the expanded conformation. So Rg value will be directly proportional to n to the power 3 by 5, which is more uh, compared to the ideal chain or the ideal solvent or the theta solvent. In the theta solvent condition, like it says, polymer behaves like an ideal chain and the radius of gyration is directly proportional to n to the power half. So the option B is correct for theta solvent or the ideal solvent. And since the chain is expanded in the good solvent, so it will be more than that, no, more than B. So the option C is correct here. Question number 18. At the most probable end-to-end distance, the distribution function of end-to-end distances shows a maximum, assuming the magnitude of the end-to-end vector to be much smaller than the contour length for an ideal freely jointed chain is given by option A. Most probable end-to-end distance square is equals to 2nl square by 3. B is nl square by 2. C is equals to nl square, and D is equals to 3nl square by 4. So let's understand the question. It is saying that at the most probable end-to-end distance, the distribution function of end-to-end distances shows a maximum. So in the lecture slides, there is one equation which is discussed about the distribution function of end-to-end distance, which is nothing but WR. So there is one equation which has already been discussed, and it says that the distribution function, which is WR, it it should be great, it should be at maximum. So for maximum we can calculate the first derivative and can equate A equals to 0, so that we can calculate maximum value of the distribution function of end-to-end distances, and then this will be at the most probable end-to-end distance, which is nothing but the value of the end-to-end distance there is equals to RMP. So after that it says that assuming the magnitude of the end-to-end vector to be much smaller than the contour length, RMP of an ideal freely jointed chain. So we need to calculate this in the ideal freely jointed chain model, where which is more likely to be ideal chain, and there the bond angles are random and they are not the fixed one. So let's calculate this. Yeah. So as we have already discussed, that distribution function of the end-to-end distance is given as WR, which is provided in the lecture slide, this formula, which is nothing but WR is equals to 4 pi beta by root pi to the power 3 r square exponential minus beta square r square, and the beta value is given as 3 by 2n L square to the power half. So this formula is already given, and it says that this question says that we need to take the distribution function of end-to-end distance shows a maximum, which means we need to calculate the first derivative, which is the dw r by dr. We will calculate the first derivative with respect to r, and we need to put it equals to 0, and for taking the maximum, first derivative should be equals to 0 for showing the maximum, and at what value of r equals to rnp, which is already said that that at most probable end-to-end distance rmp we need to calculate the value. So let's first do the first derivative we will take of this equation, which is dw r divided by dr with respect to r. From this equation, there are two r values. One is outside the exponent and r square is, and then one is r square inside the exponent. So first we will take the derivative with respect to outside r square, and then afterwards the inside one, which is in the exponential function. So let's just do it. So r square, when we differentiate, its value will come as 2r. So 2 will multiply with 4, which will give 8 pi beta by root pi to the power 3. Then 2r we got already, right? So 2 we multiplied, and r now we can write here, then exponent, and then the same minus beta square r square. The second part is, now we will take the derivative of the exponent minus beta square r square. Beta square we will take as a constant, and for r square it will be 2r, will get 2r. So minus, since there is this minus, so minus 2r, so minus 4 into 2, which is 8 pi beta by root pi to the power 3, then beta square, and r square was already there, and then 1 r multiply is r cube, and then inside function exponent minus beta square r square, which we will compute, which we will equate to 0. So now solving this, simplifying this, we will get 1 minus beta square r square equals to 0. In place of r square, we'll put r equals to rmp. So 1 minus beta square rmp square equals to 0. From this we can get rmp square equals to 1 upon beta square. So we can get put the value of beta from here to in this, and we can get 2nl square by 3. So the option A is correct, which says that rmp square equals to 2nl square by 3. Let's move to the next question. Question 19 assumes that the unperturbed dimension of the polystyrene chain. So in this question, polystyrene chain is there and it can be represented using the hindered rotation model. Now take the carbon-carbon bond length to be carbon-carbon bond length is given 1.54 angstrom and the angle is also given which is as 70.5 degree. Cos phi value is also given which is 0.65. Now the expansion parameter is given which is for the polymer when the polystyrene chain is mixed in a solution it will expand. So its expansion factor is 2.5 which is given as we already discussed that it is a good solvent, that's why it is expanding. Polystyrene chain is expanding. The root mean square end-to-end distance we need to calculate for the polystyrene chain. This we need to calculate. Which is having n value as 10,000. So what these are different options 783 angstrom, 983 angstrom, 1183 angstrom and 1383 angstrom. Let's just solve this question and see which option is correct. So we have already CC bond length as 1.54 angstrom, bond angle theta as 70.5 angstrom, cos phi value is given directly as 0.65 and then expansion parameter is given 2.5 and n value is given which is 10,000 and it is given in the question that it is a hindered rotation model. So for hindered rotation model we need to calculate all these parameters. For calculating the root mean square value which is nothing but it will be for that we need to calculate from this formula we need to calculate characteristic ratio. So for hindered rotation model we already know that the characteristic ratio will be 1 plus cos theta divided by 1 minus cos theta multiply by 1 plus cos theta divided by 1 plus cos phi divided by 1 minus cos phi which is the torsion angle. So for characteristic ratio theta value equals to 70.5. So 1 plus cos 70.5 divided by 1 minus cos 70.5 multiply by 1 plus 0.65. So it's already given cos phi value divided by 1 minus 0.65 which is equals to we will calculate and we get characteristic ratio as 9.4385 as characteristic ratio. Now unperturbed root mean squared end-to-end distance we can calculate by this formula which is the nothing but root of characteristic ratio into n into L square. We'll put all these values like the characteristic ratio we can put from here and then n value is already given in the question, L value is also given in the question. So we can calculate this and we can get 473.1 angstrom as the unperturbed root mean square end-to-end distance. For calculating the actual root mean square end-to-end distance in the solution, we can take like it's the actual mean square. Here before we calculated unperturbed because in that we calculated without the interaction of the solvent. Now we are taking into the consideration the effect of the solvent which is expanding the polymeric chain. So R square, so root mean squared end-to-end distance will be expansion coefficient into unperturbed root mean square end-to-end distance. So from this formula we can see 2.5 into 473.1 which we just now calculated which is equals to 1.83 angstrom. So it is the option C, which is correct. Now let's discuss question number 20. The size of a coiled polymer chain in a dilute solution is Rg in a good solvent, Ri in an ideal solvent, and Rp in a poor solvent. Select the correct order of sizes. So there are like a polymeric chain is mixed in a dilute solution, and then uh, when it is mixed in a good solvent, Rg is the radius, is the size, sorry, and in the ideal solvent, Ri is the size of the coiled polymeric chain, and Rp is in the poor solvent. So what should be the order? Option A says that in a good solvent, the size is more than ideal solvent than the poor solvent. Option B says in the poor solvent, size is more compared to ideal solvent than the good solvent. In option C, it says poor solvent is having more size than the good solvent, then the ideal solvent is having the least size. And option D says the poor solvent is having the size lesser than the Rg, which is in the good solvent. Then in the ideal solvent, the size will be the maximum. So just now we discussed this concept when the polymeric chain is mixed in a solvent, how it behaves. So please tell what should be the answer. So the answer is A, which is the size of a polymeric chain is more in the good solvent than the ideal solvent, and then least in the poor solvent. As we can see in the figure which is on the right hand side, that when a polymeric chain is mixed with the good solvent, the solvent will go inside the polymeric chain, and the chain will be expanded, and it will be in the like the chain will be far away, and it will be in the maximum, like the expanded form. While when it is put in the theta solvent or the ideal solvent, the chain will be like this, chain size will be the same as before. But when we put in the poor solvent, since chain doesn't like the solvent, so it will be entangled in the entangled form or the coiled form. So the option A is correct. In the poor solvent, we can see the dimensions are very much less because it is in the coiled state. So let's talk about that in the theta, what is like in the theta solvent, what happens is the theta solvent segment to segment, and segment solvent interactions are basically balanced. So polymer will be in the unperturbed state. It will not be neither in the expanded form or nor in the contracted or the coiled form. Now, yes, so today we have discussed the basics of the polymers, and it's discussed about its types, like we discussed about the homopolymers, the copolymers, linear polymeric chains, branched polymeric chains, and the applications where this polymer has been applied, like used in our day-to-day life. So after that, we discussed about the molecular weight of the polymers, which are number average molecular weight, weight average molecular weight, viscosity average molecular weight, and then Z average molecular weight. After that, we discussed about the degree of polymerization, and then the polydispersity index, which is MW by Mn. And then we discussed about the two different types of isomerisms, which are the configurational isomerism and which are the constitutional isomerism. In that, we also discussed about the geometrical or the cis-trans isomerism, and we discussed about the stereoisomerism. We discussed about the tacticity, the isotactic, syndiotactic, and atactic, and how these conformations, these will affect the final property of the polymer. Like if isotactic is there, then it will be having more packed structure, and because of the more packed structure, there will be the high crystallinity, high melting point. So we discussed afterwards the different polymeric chain models, like we discussed about hindered rotation model, freely jointed chain model, freely rotating model, and last we discussed, and after that we discussed about the chain dimensions, like the contour length, the radius of gyration, cone length, and then mean square and twin distance. We discussed about all these, and then finally we discussed how a polymeric chain will behave in a solvent, in a good solvent, in an ideal or the theta solvent, or in a poor solvent. In the next week, we will try to discuss the week 2 topics, which are thermodynamics of polymeric solutions, and then Fleury-Huygens theory, which is very much important, then phase behavior, afterwards the miscibility and solubility parameters. So, in the next class, we will discuss all these. So, after this class, I'll be uh, putting this recording in my YouTube channel, on my YouTube channel, and the link is provided here. You can go to this link and can see the recorded lecture, and this PPT will be shared in the Google Drive link, and the Drive link is also given. Also, my email ID is shikha.s.cl at iitguwahati.ac.in, and you can write to me your doubts, so that we can discuss your doubts in the next lecture. What we will be doing is, we'll be first taking up your doubts, and then we'll move to the week 2 lecture problems. We will practice those problems, and we'll try to solve, uh, and please join the next lecture on the next, which is on the next Sunday. So thank you so much for listening and connecting. Now, this is the end of the lecture. You can leave, please leave the meeting. Thank you so much.